morning, everyone. This session, thank you for giving me an opportunity to chair this session. This includes this is a pre-tea break session, includes two important talks. The first one is by Dr. Anjan Barman, and the other one is by Dr. Anand and Sharma. So I invite Dr. Anjan Barman, who will speak on spin texture drive-in magnetization dynamics in engineered magnetic nanostructures. Dr. Barman, please.
Okay, good morning everyone, and thanks to the Indian Academy of Sciences for inviting me to give this talk. Today I'm going to talk about spin texture driven magnetization dynamics in engineered magnetic nanostructure. I'm from the Bose National Centre for Basic Sciences in Kolkata. So the world of spintronics has come a long way from this conventional read-write drive and magnetic random access memory to the spin orbit torque driven random access memory, magnonics that I will describe today, like magnon transistor and various other components have come up. Terahertz spintronics and ultrafast all optical writing of bits in the femtosecond time scale to picosecond time scale, because the conventional one is still in the nanosecond time scale. So you have to go much faster, and then atomic based spin based logic devices and so on. So it has come a long way till then. So that requires the magnetization to sort of be manipulated in a very fast time scale, and so we'll go through the time scales of magnetization dynamics, and here I show from femtosecond to microsecond, like 10 to the minus 15 to 10 to the minus 6 seconds, and the most fundamental exchange interaction, Heisenberg exchange interaction, fall in the femtosecond time scale. Spin orbit coupling comes in the hundreds of femtosecond time scale, and the laser induced ultrafast demagnetization that I will describe today falls in this time scale. And then also the spin transfer torque and spin orbit torque, they come in the sort of femtosecond time scale. This is followed by the precession of magnetization, which is not the Larmor precession of a single spin, but the precession of the full collective magnetization, followed by its Gilbert damping, and then magnetic writing, vortex core switching, they fall in this time scale. This followed by the spin waves, which is the collective dynamics of the spins in the system, and the domain wall motion. So I will talk primarily the laser induced ultrafast demagnetization and the magnons in this talk today. So the ultrafast demagnetization was first discovered in 1996 when Borpier and Bigot, they actually shined a femtosecond laser pulse on a nickel film, and they showed that the magnetization was quenched partially or sometimes fully in presence of the exchange interaction and a magnetic field. So that was called ultrafast demagnetization. This was followed by the recovery, and they came up with a 3-temperature model where the electron spin and the lattice system come into non-equilibrium with each other and they interact with each other. And you can define temperatures corresponding to the three systems, which rises and decays in their own time scale. And you can see here the electron temperature rises first, followed by the spin temperature, and the lattice temperature is growing much slower. So there have been classes of thoughts of describing this, and the debate is still ongoing. And the first one was the spin flip scattering, which was first thought to be a phonon mediated Elliott-Yaffe type spin flip scattering. But later on, electron magnon, Coulomb exchange, and even relativistic photon-induced spin flip scattering have been considered. And then later in 2010, a new transport process-based mechanism came up, where the super diffusive spin transport, which is governed by these laser-excited hot electrons to play a crucial role in the ultrafast demagnetization through this spin-dependent transport. And here you can see that this mean square displacement is proportional to the t to the power gamma, where gamma corresponds to 2 is a ballistic transport, which occurs in the shorter time scale, and 1 is in the diffusive transport that occurs in the longer time scale. But it actually occurs somewhere in between, like gamma is between 1 and 2, and that is why it's called the super diffusive spin transport. And that was given by this paper. And then more recently, optically induced spin transfer effect also thought to be playing a role. Now, considering all these effects, primarily the spin transport effect is coming up to be one of the most dominant effect in the recent times. And there one can see that if you have a domain wall in the system, then the domains of two opposite spins can act as two different spin channels. Like this can be the up spin channel and the down spin channel. You can call this the majority and the minority spin channel. And in these two papers, it was observed that in comparison to the uniformly magnetized system of similar composition, a much faster demagnetization or accelerated demagnetization occur due to the direct transfer of spin angular momentum between the neighboring domains. So they act as two different spin channels, like we said. So what our goal is to see what happens. So they were working only on these stripe domains. We wanted to see what happens to the ultrafast spin dynamics if the domain wall can be tailored over a wide range of pattern. And that's what we did here. So what we did here, we took a cobalt palladium multilayer. It has a perpendicular magnetic anisotropy, and it also has a demagnetizing field. So just by controlling the magnetic field history, like we have listed here, so we first took the AC demagnetization, and we got this kind of stripe domain with some junctions here. And then we apply a 2 kilohertz radiant plane field, and we remove the junctions, and we have perfectly parallel stripe domain. And then we apply a 14 kilohertz out of plane magnetic field. We obtain this labyrinth type of domain, and then we apply a 6 kilohertz out of plane magnetic field, and we obtain this kind of bubble domain, and we refined it further. So we are going from a purely one-dimensional domain structure, a two-dimensional domain structure here, and the Fourier transform of those can be shown here. Here you can see just two spots, like the lowest spots here, and here you start to see a full circular pattern due to this two-dimensional structure. So we want to see what happens when we actually go from or transit from this 1D to 2D domain structure in the ultrafast demagnetization. So we use the time-resolved magneto-optical Carr effect magnetometer. So this is based on a femtosecond pump probe technique using a femtosecond amplifier laser, and it's a two-color measurement. So we use the second harmonic generator, and this is a time delay, and this is the sample here. So you can see the two color. The pump beam is falling as an oblique angle, whereas the probe beam is falling on the sample normally. So we are measuring the polar Carr rotation. So it has a time resolution of 40 femtosecond. Spatial resolution is not important here. It's about 200 micron, and the pulse energy repetition rates are like that. And here we can also access various wavelengths from 250 nanometer to 2200 nanometer. So first we consider the power spectral density of the domain walls, and here you can see that we fit this with the asymmetric Lorentzian equation, and we found out the average wave vector delta k, the domain wall width, and this is very important, the number of domain walls per 100 micron square. And we can see that as we are going from the linear to the two-dimensional domain, the domain wall junction increases enormously from 100 to about 2000. So this will have a role to play, as I will show here. So we measure the ultrafast spin dynamics in this multilayer. First we measure the sample with no domain, and this is the measurement geometry. And here I see the negative delay followed by a fast ultrafast demagnetization in femtosecond time scale, followed by the recovery and the precession or the spin wave generation, which is very normal for a thin film. So here we have no domain. We fitted it with a 3-temperature model, and we found that the demagnetization time and the recovery time, they're increasing almost linearly with the pump fluence, and the quenching is also increasing with pump fluence. Fine. Now we go to the domains, and here you are, and you can see here, as soon as I have the stripe domain, in addition to the ultrafast demagnetization, it recovers and it actually crosses the saturation magnetization, and it increases. So you are actually generating magnetization by the laser pulse, and this is called the transient magnetic generation or enhancement in the picosecond time scale, and then it slowly recovers. When you go to the labyrinth domain, the demagnetization part actually reduces, but the transient magnetic enhancement remains the same. And as you go to the two-dimensional bubble domain, the demagnetization completely disappears, and you have only the transient magnetic enhancement. So there is a drastic change from a two-step to a single-step spin manipulation in the system, and this remains sort of consistent with the pump fluence. So if I change the pump fluence, only the magnitude and the time changes, but qualitatively they remain the same. So we try to understand why this is happening by developing a spin transport model, a hand waving model of course. So we took the domain walls, let's say we have the stripe domains only, and we are pumping and probing the domain walls. So initially we have two different channels. This is, let's say, the down spin channel and the up spin channel. And we know that there is a direct transfer of spin angular momentum between the domains, and we know that the majority carrier mobility is higher than the minority carrier mobility. So as we are pumping it, this down spins will cross the barrier, domain wall, go to this orange side, whereas the up spin will cross this and go to this side. And as a result, you will have more down spin here that will cancel the up spin and reduce the magnetization. And similarly, it will reduce the magnetization here, and you'll have a partial demagnetization. However, this occurs in the femtosecond time scale. In the picosecond time scale, the minority carrier from here comes back to here and from here to here, and while doing that, it also brings back some of the additional minority carrier, which was the majority here to here and to here, and as a result, you will have more downspin here and more upspin here, and that will increase the net magnetization in the two domains, and you will have a transient magnetic enhancement in picosecond time scale, and after that, they will again come back to their original position and have magnetization recovery. So that is why you see first the demagnetization, followed by the transient magnetic enhancement, and then the recovery. Now, question is why you have only the transient magnetic enhancement in the case of the bubble domain. That is because in the case of bubble domain, you have a really disordered system, and the net magnetization here is very little, almost negligible, as opposed to here. And as a result, if you have almost no net magnetization, so there will be no demagnetization as well, only the transient magnetic enhancement. And also, we will model it using this three temperature or T3 time model. So here tau m is the demagnetization, tau TME is the transient magnetic enhancement, and tau r is the demagnetization. And we plotted them as a function of pump fluence, and they all increases with pump fluence, and they changes with the domain wall sort of pattern. And this is very important. Here you can see both the magnetization quenching and the demagnetization. And this is like the stripe domain, and you can see the quenching and the demag time is much higher. And as you go to a higher domain wall density, you reduces the demagnetization, and here the demagnetization almost becomes zero because the disorder becomes more. And here also you see that where the transient magnetic enhancement actually shows the opposite trend. That is because you have more number of junctions through which the spin transport can occur. So here we observed a stark variation of the leisure-induced magnetization response during transition from 1D to 2D domain configuration, and that demonstrates a transformation from a two-step to a single step like transient magnetic character, and that can be used for a two-step switching operation in ultrafast spintronic devices. And this paper has just been published. Next we come to the magnonics. We know that for spin transport there is a transfer of spin from one place to another, so there will be scattering and all this, so that causes energy. Whereas for spin wave, there is only transfer of energy, there is no transfer of a particle. Of course, there is a quasi-particle associated with it, so spins precess in their own position, and their phase is propagating through the medium in 1D, 2D, and 3D. And based on that, we can develop different kind of artificial magnetic medium or the magnonic crystal, which can give rise to different kind of band structure. And I can show you here some band structure with this one-dimensional array of antidots with band gaps and so on. So magnonics basically deals with this propagating spin wave through periodically modulated magnetic media, which has enormous application in gigahertz to terahertz frequency on-chip data transfer, logic, and various other devices. And here you can see some of the examples here. And the last one is the voltage controlled magnetic logic, because one of the important characteristics of this is external control on the devices. Whether you can control it, because once the device is made, you cannot control it by changing its structure. you can only control it by the external stimuli like electric field, magnetic field, and so on. So whether we can do that. So here we propose to do voltage control magnetic anisotropy, and here one can use the ultra thin ferromagnetic and insulator bilayer. And what happens here for a ferromagnet, you have the out of plane orbital of ferromagnet like the 3d z square and the 2pz orbital of the oxygen, and they actually sort of overlap and cause a significant charge transfer from 3d z square to 2pz orbitals. That gives rise to a sizable perpendicular magnetic anisotropy through spin orbit coupling. Now if we apply an electric field in this junction, then the number of electron in the outer plane 3d orbital of the ferromagnet is changed as compared to the 2pz, and as a result there is a change in the perpendicular magnetic anisotropy, and that is known as the voltage control magnetic anisotropy. And linearly you can actually express it as delta Ks, that is the change in anisotropy, as beta times Eg, where Eg is the electric field and beta is the voltage control magnetic anisotropy coefficient. And one can actually use this not only to change the anisotropy but to create different type of spin texture, reconfigurable nanochannels for propagating spin waves. That is something that we will do it here. So this is a voltage control magnetic anisotropy based magnonics. So we developed this system. So this is cobalt iron boron and MgO that gives the VCMA or the PMA, and then we actually build an aluminum oxide, and then on top of that we build an ITO based top electrode, where here the gold is the bottom electrode, and we apply a voltage, a gate here. So basically this electric field penetrates through this junction, and it actually causes a change in the electron occupation at the 3dz and 2pz orbital of the ferromagnet and the magnesium oxide, giving rise to the VCMA. Now here you can see that this pattern, there is no pattern, this is continuous. So the electric field will continuously penetrate and give rise to an uniform change in the anisotropy. So when we do this Brillouin light scattering measurement, we can see that there is a shift in the peak of the spin wave as opposed to this dotted line, which is for 0, v equals to 0. So when I apply +4, it shifts on the positive side, and -4 volt, it shifts on the negative side. So you know that the VCMA is working. Now we do further characterization. So this is the magnetization, this is roughness profile, and so on. And here we actually find out, as a function of gate voltage, the change in the anisotropy, and which changes linearly. And from there we found out the coefficient, VCMA coefficient, which is reasonably high. And this is the frequency versus wave vector for this continuous, for this device. So there is a single mode, single spin wave mode, which fits with the Demon-Eschbach geometry. Now we do this. Now what we do is we pattern the ITO electrode, and this the width of this pattern is, so here you can see it is about 200 nanometer. So you have 200 nanometer of ITO, and then there is a gap of 200 nanometer, and so on. So when you apply and then connect these all to the bottom gate gold electrode, and when you apply the electric field, only the electric field appears beneath these ITO electrodes, and where there is no ITO, no electric field is there. So you essentially sort of on demand, you can change the spin texture of this sides as opposed to the remaining sides. So you actually create 2 nanochannels through which the spin waves can propagate. And when you do the Brillouin light scattering measurement of the spin wave, you can clearly see that the single spin wave mode actually splits into 2, and here for another wave vector, and you plot them as a function of wave vector, and you can see that yes, clearly there are 2 modes with a band gap. Okay, so we actually can open a band gap, and as soon as we switch off the voltage, the electric fields will disappear, it will not matter anymore, and we'll have the single mode. So you can on and off the the band gap just by controlling the electric field here. And when we do the numerical calculation by using plane wave method, we see that through channel 1 only the spin wave mode 1 is propagating, whereas through channel 2 spin wave mode 2 is propagating. And there is a mode repulsion due to the magnon-magnon coupling in these 2 channels, which is giving rise to the avoided crossing and the observed magnonic band gap. And this is for another wave vector. And this is the reconfigurability when I apply a minus, earlier I applied minus 4 volt, when I apply a plus 4 volt, I can see the band gap changes from 1.3 gigahertz to about 0.9 gigahertz. So the band gap is reconfigurable, although the behavior is essentially qualitatively the same. So here I show further reconfigurability of the nanochannel. So if I do not apply a voltage, I have a single mode. If I have only the reference coffee B and MgO without any top electrode, I have a single mode, and these are the wave vector dependent frequency. So that gives the reconfigurability of these nanochannels, which gives rise, and this will give rise to the parallel processing of modes through the for classical and also quantum computing, because the magnon-magnon coupled hybrid modes, they can coherently propagate through over a long distance on chip and give rise to sort of a quantum computing platform. And that appeared in the media for novel design of magnonic nanochannels, which may cut down cost of transferring electronic signals, also Nature India, and so on. So in summary, I have shown you how different domain walls can cause different types of spin transport and sort of give rise to ultrafast spin manipulation from demagnetization to transient magnetic enhancement. I've also shown that how one can tune the voltage control magnetic anisotropy to give rise to different kind of magnetic nanochannels for spin wave propagation. And this is my group. I thank you very much for this wonderful work, and thank you all for your kind attention.
We can have few questions. We still have few minutes. I forgot to mention Dr. Barman was elected to the as the fellow of the Academy in 2020.
I have one simple question. You have shown 9 domain patterns over there for several samples, like stripe-like and then bubble-like and all. So domain wall thickness you mentioned is between kind of 100 nanometer to 200 nanometer.
Yes, something like that.
So what should be the thickness of that top layer where you have measured this?
You mean the cobalt layer?
Yes.
That is about sort of less than a nanometer.
Thickness is less than 1
nanometer. The width of the domain wall is 100 nanometer. This is a lateral width.
Okay.
And the thickness that is in the z direction, that is about a little less than a nanometer.
So does it demagnetization, does it depend on the thickness in any
Yes,
way?
yes. The demagnetizing field depends on the thickness.
Right, right.
And
even
also
time
there
scale,
is, yes, and there is a perpendicular magnetic anisotropy at the interface of cobalt and platinum due to the DD band hybridization.
Yeah. So substrate effect is also there.
Substrate effect is there, but here, because it's a big stack, so it is sort of, the strain effect is relieved.
Relieved at nanometer thickness?
Yeah, within few layers it is relieved. There is very little strain, and that is relieved within few nanometer.
Okay.